Good afternoon, everyone. It's January 16th. February 16th. What is it? February 16th, 2021. Please put in the attendance what you think sucks the most about COVID in the chat, for attendance. So many things to choose from. How will you decide? I don't know. So just pick something if you can't decide. So while people are doing that, tell me, how are breakout rooms going? Are they working? Are they not working? Do you have enough time?
I think the breakout rooms are doing, it's a really good way to teach the class. I think it's good.
Okay, cool.
Yeah, I think it works well. I think the only issue I've been coming up with is running out of time, but that's more on our end than anything.
Yeah, I
Okay.
agree with Alex. It's just that sometimes we run out of time.
Okay, is the running out of time getting in the way of the learning?
I don't think so.
Brendan?
No, I don't think it does either. I'm just a perfectionist.
Okay. Anybody else? Positive, negative, neutral? Feedback on breakout rooms.
I like the breakout rooms. I use them in some of the other classes too, and I enjoy being able to hear what other people think.
Okay. Well, keep giving me feedback. If you feel like you need more time, we can do that. Or maybe I need to shorten the problems or something too. I can try to make them, not multi-part or whatever, if we need to. Excuse me. Okay, any other feedback or questions? Okay, so if we look at the website for this week, we're in week 5. We've made it to week 5, everyone. We're going to be finishing up mean and standard deviation and also talking about histograms and distribution functions, which makes sense because you're basically repeating the same thing over and over again and then thinking about it for all of these. Thinking about it in some way, like mathematically, for all of these concepts. So if you look at the week for this week, we're going to first do this example today because we need to talk about discrepancy. That's a item that we didn't finish last week. That's included in chapter 3. And then we'll go back through a little bit of the mean and standard deviation stuff we saw last time and a little bit more new stuff and work on some in-class problems. And these are already posted for this week. So if you want to go ahead and get started early on those in-class problems, you can have them kind of worked on before we get into the breakout rooms. But also don't feel like you have to do that. The point is to work on it together. But they're there in case you want to get started early. Okay, that's it. I'm going to keep going unless there's questions. Okay, so we're going to look at the problems from last week. So the in-class problems 2.9 and 2.11. We're looking at the last one about the current balance. So I will let you refer to that problem there to know what is the problem that we are doing. So go to the As You Learn page to read that. I've kind of repeated the information in my version of it. So I posted the solution to that here in this week. Example to explain discrepancy current balance problem from 2.9 to 11. So if you click on that, you can follow along with me here if you want, or look at the actual problem, or look at the screen while I'm doing it here. So we know that the accepted value for the permeability of free space is 4 pi times 10 to the minus 7 Tesla meters per amp here. And that is, I've converted that to something with an arbitrary number of sig figs here just to see what the actual value is. And someone measures mass, current, length, and radius in order to determine this mu naught experimentally in a fun physics experiment in their class with this apparatus. We're not really worrying about how that works so much. We just know that they measure mass, they measure radius, they measure length, and they measure current. Those are the measured quantities. And then we can calculate a measured version of mu naught from those values. We also know g is the acceleration due to gravity. We're going to assume that the 2 pi in the equation and the g in the equation have no uncertainty. They're perfectly certain values, so they don't affect our uncertainty calculations. We are told that the uncertainty in the mass is 1% of the mass. And we are told that the uncertainty in the current is 2% of the current. We are asked to find, sorry, I forgot to mention that. We are asked to find, let's go back to that problem here. All right, so in part A, we're asked to find the propagated uncertainty and the final value of permeability of free space, measured value. And they give us these measured values of 20 milligrams and 5.63 amps. Then in part B, they ask us, what is the discrepancy and is it significant? So those are some things we haven't really covered yet that we're going to cover in this example. All right, so based on the given uncertainty values and the measured values, the uncertainty in the mass is 1% of 20 milligrams, so 0.2 milligrams. And then the uncertainty in the current is 2% times the current, so 2% times 5.63 amps. I converted the 0.113 amps to 0.2 to get 1 sig fig for my uncertainty there. My measured value for L with its uncertainty was given as 26.50 plus or minus 0.02 centimeters. Measured value for R is given at 0.80 plus or minus 0.05 meters. Any questions so far? So given those above values, I'm just going to scroll down so you can see this whole thing. Given the above values, we're supposed to find the measured version of mu naught based on the measured quantities and the uncertainty in that measured value version of mu naught, that magnetic permeability of free space. So here's the equation rearranged so that we have just mu naught equals stuff. And I have emphasized what are the measured quantities here and what is constant. I rearranged it to put the constants up here on the top left all together that do not really affect our uncertainty or our uncertainty propagation. And then all of these are going to be measured quantities, M, R, L, and I. So I substituted the quantities and I got 1.197 times 10 to the minus 6 Tesla meters per amp. So please check my math. Don't just trust my math. Everyone, do your own version of that calculation. I'm keeping all the sig figs for now because I'm going to wait till the very end to figure out how many sig figs I really get from my uncertainty. I didn't show that yet here. Okay. Because this is not like a function of something, it's just like a single value situation. I used the uncertainty divided by, I use the fractional uncertainty here that we use for like products and quotients for numbers, for variables. So we add up all the fractional uncertainties of the measured quantities. I think I substituted all these in correctly, so please check my math. And I got 0.0726 for that fractional uncertainty of for the magnetic permeability of free space. It gets kind of small down here, but then I basically I just multiplied 0.0726 times mu naught to get delta mu naught here, which is 8.69 times 10 to the minus 8 Tesla meters per amps. Still just carrying an arbitrary number of sig figs through until the end. So I rewrote our quantity here as 0.09 times 10 to the minus 6 Tesla meters per amp. And that gives us, that allows us to see that we can convert our measured quantity of 1.197, our measured version of mu naught, to 3 sig figs. We get to keep 1.20 times 10 to the minus 6 Tesla meters amps. That's why I made this change here, just so I'm looking at the same times 10 to the whatever for the value and for the uncertainty. Okay, questions about that? That was like review. We know how to do all that already. Did I do it right? Anybody have?
Dr. Hester, I was going to ask, for the I squared, for the amperage squared, why did you not use that formula that was for the Q is equal to X to the N, where you have N times the like dx over X, I guess?
Yeah, I forgot a 2 there, didn't I? I forgot it was squared.
Oh, okay. Okay.
So there should be a 2 in front of this delta I over I.
And then I have a question.
job,
So for the current, it's like 5.63 amps, and we determined that the uncertainty was 0.2 amps. Would we need to round up the current to 5.6 amps? Or round it down for that?
Yeah,
And
to
then
make
plug it
those
in?
have the same precision.
Yeah.
I believe we are supposed to leave the measured quantities, all the precision in until the very end.
Okay.
The uncertainties we round first, though, up to one sig fig.
Okay, that makes sense. I just wanted to ask.
Thank you. And yeah, that is supposed to be times 2 inside the parentheses, but we're going to continue for now as if there's not supposed to be a 2 there, just so we can do part B. I don't think it'll make that much of a difference. So let's just go with this 0.09 times 10 to the minus 6 Tesla meters. I'll fix this and upload it again. In part B, the question is this a significant discrepancy? What is the discrepancy? Is part B. What is the discrepancy, and is it significant? Okay, so discrepancy is how different is it from another value? Literally, the difference. Where'd this go? Sorry. Somehow I got scrolled. All right, so to find the discrepancy, we literally take the accepted value and subtract the measured value and take the absolute value. It is literally the difference of those two quantities. Okay, so I rewrote that here. Let's expand this all the way. I rewrote my measured quantity also as a range, because that's going to be helping us to answer, is this significant or insignificant, this discrepancy? That question, is it significant, means, is the accepted value within this range? There's a range here of values that our measured quantity could be. That's what we're saying. We don't know if it's for sure actually 1.20 times 10 to the minus 6 Tesla meters amps. It might be anywhere in this range from 1.11 times 10 to the minus 6 Tesla meters amps up to 1.29 times 10 to the minus 6 Tesla meters amps. Is the actual accepted value in that range or not? That is what we're asking here. So I did a little map, kind of like your book does. Here's the range of values along my y-axis that are being talked about in this example from UNOT. The accepted value is up here at 1.26 times 10 to the minus 6 Tesla meters amps. Notice I put the times 10 to the minus 6 in the axis label. It's not in every single number here. This is actually kind of like too many numbers, but just wanted to be able to see the values. X-axis has no meaning here. We're just talking about Y values. Our accepted value is here at 1.26. Our measured value is down here, centered at 1.20, but could range from 1.11 all the way up to 1.29. So the accepted value does fall in that range. So that means our discrepancy is insignificant because the accepted value falls within the range of the measured value, plus or minus uncertain. It is very important for you to do this at the end of your experiment, whatever your experiment is. If you're measuring an accepted value, measuring, a measured value and then comparing it to the accepted value, you should think of it in this way. If you're only measuring measured values and don't have like an accepted value to compare them to, then you just repeat this and then all your measured values have error bars. And if their error bars overlap each other vertically, then that's an insignificant discrepancy. But if the error bars do not overlap each other, that is a significant discrepancy. And when you have a significant discrepancy, that is a problem that needs to be fixed. Any questions? Okay, so the homework due this Thursday. We'll have some questions about discrepancy. So I think you're now prepared to answer those. And everything else that is in that homework this week. Okay. Questions before we move on? Darn it, sorry. Okay. So next, we're going to go back to our mean and standard deviation lecture. And I'm just going to review really quickly a little bit of stuff. So can y'all see that okay? Yes, okay, I saw some. All right. So when we measure something as physicists, we don't do it one time. We don't do it 2 times or 3 times. We do it a whole lot of times. And this is why. Because if we have random error I guess not just this slide, but if we have random error, one of the topics on this slide, then the more measurements we make, the less that error is going to matter. We have some control over that random error. We can like defeat that random error if we take enough measurements. And we know it's random if it's evenly distributed around some kind of central measurement, around that accepted value. So here's an example where we have someone measuring a whole bunch of values, doing a bunch of measurements of some value. Red is the accepted value. Blue are the measured values. Here we have in the most left-hand version, we have values that are not distributed around this center point. We also have values that are not distributed very far from each other. So there is some randomness here, but it's not large, it's small. So we have a small statistical error. We could make it smaller if we took more, we could like make that, those condense into a smaller point if we took more measurements. But just taking more measurements is never going to help us get the center point to match up. That comes from a systematic error. So we have a systematic error causing our measured value to be off, mostly here. In this case, the next one over, these points are very spread out around from each other, far from each other. So there's a whole lot more randomness, a whole lot more statistical error happening here. They are not centered off of the measured value. The center point is still lining up with the measured value. So we have a small systematic error here. If we took a lot of more measurements, a whole lot more measurements here, we would eventually get rid of that random error. And we would measure that center point with pretty high precision. Oops, sorry. Here we have large random error. Because we have a lot of the points spread far away from each other. We also have large systematic error because the points are very not centered around the correct value. If I was to take a whole lot more measurements here, I would reduce, again, that random error and get those points to be smaller, get closer to each other, like surrounding some kind of common value more and more, closer to it more and more, if I increase the number of measurements. But that's never going to help me get that center point closer to the real value. I have to fix that systematic error to do that. And here I don't have a lot to fix. I have small systematic and random error, but I still could reduce my random error by taking more data points. Okay, any questions about that before we go on? Okay, so we're going to talk about random errors for the rest of the day today. We're not going to talk about systematic errors at all anymore. We were talking about both, so we know what they are. Now we're just focusing on random errors. So that's what you saw this slide a bunch of times already, but that's what it was about. If we take a whole bunch of data points of noise, in this case, this is like a voltage fluctuation, then if it is truly random, if the wrongness of my value, the incorrectness of my measurement is truly only based on randomness, on the statistical effects that we're seeing here, then that means there's just as many data points above as below the average value. So the average value here, it's hard to see. These are like numbers, this dark thing. And then just above that is the average value. There's just as many above as there are below. And if there's not, then that means something systematic's going on. If there's not something systematic going on and noise is your only contributor to the only true contributor to your uncertainty, then you can reduce that uncertainty by taking more data points. So we defined this last time, I think, but here it is again. The mean is going to be the average, the central value of those data points. So n is the number of points. And you add up the points and you divide by n to get the average. So x sub I and x bar should have the same units. Okay, so what is the uncertainty for one data point in your set? If you have a set of data points, the uncertainty in one data point is the standard deviation. And we have sigma sub x because that's like the set that we're talking about. The residual is how different is the actual value, is each value, from the mean value. So how wrong is x sub I? How far off is x sub I from mean? Is that residual? And then the standard deviation is going to be a sum of the squares of the residuals times 1 over n minus 1. Okay, here's one more definition. That was the sample standard deviation for smaller data sets. If you have a huge data set, then n minus 1 and n are basically the same thing. So for huge data sets where n is equal to like 100,000, that's not really going to change if you have 1 over 100,000 minus 1 is about the same as 1 over 100,000. So for a large data set where n is very large, you can use this simplified version without the, without the minus 1 in the denominator. So I'm going to go back one more time again. Here's the general definition for the standard deviation, which is the uncertainty in one data point from your set of measured values. And the standard meaning has this n minus 1 in the denominator, but if n is big, then minus 1 doesn't matter. Questions about standard deviation?
Do we decide how big is, or is there like a set value, like thousands?
Well, we can kind of talk about it now. So if n is 10, right? If n is 10, let me make this go away. If n is 10, then 1 over 10 compared to 1 over 9, that's pretty different. Those are two pretty different values, right? Or let's just say n is 4, whatever, just to make it more extreme. So 1/4 compared to 1/3 is 0.25 and then 0.33. So that's going to significantly change your standard deviation if you don't include that 1 for smaller data sets. And then let's say n is equal to 400. So 1 over 400 is 0.0025. And 1 divided by 399 is 0.0025 0.06. So that's pretty much the same. That's not going to affect your standard deviation if you don't include the -1. If it's 400. So you don't have to get it too big for it to not matter. But let's see why we have this whole -1 in the first place. Look at this paragraph down here at the bottom that I'm circling with my mouse. The point is that if n equals 1, if you only make one measurement, then you get 1/0 equals infinity for your uncertainty. If you make one measurement, your uncertainty is infinity. That's why that n is there. It wants to make sure you make a lot of measurements. And it wants to account for the fact that the more measurements you make, the smaller your uncertainty is. That's how we get that to happen. So thank you for asking, Brendan. Okay, now we also have the standard deviation of the mean. That is different than the standard deviation. Okay, so be careful. Don't mix those two up. Standard deviation of the mean has a new symbol. It has a sigma sub x with a mean over it, with a line over it. And the standard deviation of the mean is the uncertainty in the mean. Okay, what we were talking about before, the sample, standard deviation, sigma sub x, or population standard deviation, sigma sub x, is the uncertainty in the individual measured value, x sub I. Now, the standard deviation of the mean is the uncertainty in the mean, x, with the bar over it. And that is defined as the sample or population standard deviation divided by the square root of the number of points. We will show why a little in a bit. It's not just like a definition. It does come from error propagation equation. Okay, so we have to calculate the sample standard deviation to get the standard deviation of the mean. Sorry. Any questions? Okay, again, our uncertainty in our mean value is going to decrease as we increase n. The bigger n is, the smaller our uncertainty in that average value. So that's nice. The less we're going to have that x, that error, random x error. That's going to get smaller as we increase n. Okay, here comes the proof that shows that that's the case using error propagation. That this is the case. The standard deviation of the mean is equal to the standard deviation sample or population standard deviation divided by the square root of the points. Okay, so there's our average equation here, and we've gone back to using now the green is the measured value and blue is the calculated value. And our uncertainty in a single value x sub I, our uncertainty is delta x sub I, which is also equal to the sample or population standard deviation in blue over there. Okay, so that is a sum divided by a constant, that average equation. right? It's a bunch of numbers added up divided by a constant. Not too crazy, not too complicated. So the uncertainty delta in the mean, delta x bar, is equal to the standard deviation of the mean. Let's go back one. Okay, equal to the standard deviation of the mean, which is equal to the standard deviation divided by the square root of n, the number of points. Okay, so we found the, we're substituting, finding first the, first we're considering the error propagation equation here for just delta x bar. So we're going to take, this is not the fractional uncertainty, so that constant does come along for the ride or whatever. So we have n times the fractional uncertainty squared of whatever x sub I is. The fractional uncertainty of x sub I is the standard deviation, the sample or population standard deviation. And then the standard deviation of the mean is equal to the standard deviation, the sample or population standard deviation divided by square root of n. So that's what we end up showing here by just plugging in our original propagation of uncertainty equation. We can basically derive this final expression here. I'm sorry that the slide keeps changing. Okay, so do we have questions about standard deviation of the mean, standard deviation, average? Anybody?
I have one question. Did you say the sample standard deviation? Yeah, the sample standard deviation is the uncertainty in each measurement of the sample?
Yes, so right here, the
Mhm.
sample standard deviation is equal to the uncertainty of a single measured value.
Okay.
And then the standard deviation of the mean is the uncertainty of the mean. Yeah.
All right, thank you.
And you calculate the standard deviation of the mean using the sample or population standard deviation. You're welcome. Other questions? Okay. Where are we on time? Good. Okay, we're going to go into breakout rooms then, and we're going to do problem 1 from the As You Learn page. If you go here to the mean and standard deviation in class problems, we're going to do problem 1 from there. So you can get started working on that, and I will paste the breakout rooms if you don't remember who you're supposed to be with. We'll put that into the chat window. Maybe it'll work today, where everybody just gets to go into a breakout. Okay, you should be able to see your breakout room assignments there. And you should be able to choose your room now. Okay, were y'all able to get to an answer? Anybody's group?
We got to we answered A, but we were a bit confused about how to do B.
Well,
Okay.
I answered A, and then with by extension B.
Okay, so can you compare your answer to what is shown on the screen now? Did you get 1.345 seconds for the mean,
Let's see.
everyone?
Yep.
Okay,
Mhm.
and for the standard deviation, I got 0.01615 seconds. Keeping all sig figs for now.
Yeah.
Okay. How about standard deviation of the mean?
Just 1.345 divided by the square root of this.
Yeah,
number.
0.01615 seconds. Sorry, I forgot my seconds here. Divided by the square root of 8. And then I just kept lots of sig figs for now, 0.005709 seconds. But we would round to 1 sig fig there if we were reporting that as this, uncertainty. I was just keeping sig figs here for calculation purposes. Okay. Supposed to stop now. I'll miss you, but I'll see you Thursday.
See you Thursday.
Good
Have a good day.
Have a great
See you
week.
Thursday.
You too.
Thank you, Dr. Hester.
Thank you.